Okay, this is part 2 of the retirement problem, where we're working with two proportions. And we've just finished a hypotheses test where we were able to conclude that more men than women feel comfortable about about the money they've saved for retirement. So the question is, how much more? So what we would need to do is a confidence interval. So the nice thing about doing a confidence interval after a hypotheses test is that the conditions have already been satisfied. So the conditions are met for a 2 proportion z interval. Okay, we're going to use a slightly different standard deviation, but in essence, the model that we just used applies, the normal model. Okay, so what we really need to do, what's different, is we need a standard error, but we're not going to pool now. So that's the standard error of p, not p hat, yeah, p hat m times q hat m over n m plus p hat w q hat w over n w. Okay, so that's the square root of, and if I recall, this was 0.27, so that's 0.73 all over 250. And then for women it was 0.18, so that would be 0.82 all over 250. Okay, so you can enter this in your calculator. Just do the square root function and don't put parentheses, just say 0.27 times 0.73 divided by 250 plus 0.18 times 0.82 divided by 250, close parentheses for the square root, and hit enter, and you'll get it'll do the whole thing. The calculator knows order of operations, so it knows to do the multiplication and division before doing the addition. So with that, what we get is we get 0.3713. At least that's what I get. Okay, so let's see. Let's think about our confidence interval for a minute. That's going to be an estimate plus or minus a margin of error. So the estimate is p hat m minus p hat w. Okay, so that's the observed value plus or minus z star times the standard error of, and I actually should have put in here, p hat m minus p hat w. Okay, so p hat m minus p hat w. Okay, so this value, the observed difference, we already computed. Here it is, 0.27 minus 0.18, so it's 0.09. So that's the observed difference, 0.09 plus or minus. Now we've got to get z star. I'll come back to that, but we already have this. This is the standard error, 0.03713. Okay, so to get z star, I'm going to say, well, we want a 94%, so 0.04, so this would be 0.02, and this would be 0.02. So I can say z star is essentially equal to the absolute value of the inverse norm of 0.02. So I can get that z value, and then I'm going to ensure that it's positive. Okay, so when I do that, I get 2.054. So 2.054. So I get 0.09 plus or minus. When I multiply that out, I get 0.076 after rounding to 3 decimal places. Okay, so there's my margin of error right here. So my confidence interval is going to be 0.09 minus 0.076 and 0.09 plus 0.076. And when I do that, I get 0.014 and 0.166. Okay, so I haven't double checked this, so I'm assuming that's right. So let's say we are 94% confident that, and then here we have to be careful, between, and it would be, let's see, move the decimal over twice, boom, boom, 1.4% and 16.6% more men than women feel comfortable about the money they have saved for retirement. Okay, so that's just sort of a follow-on. Now, whenever we do a confidence interval, let's just check consistency with the model. So originally our hypothesis was that the difference was 0. Okay, so we notice that this confidence interval does not include 0. Here's our number line. Okay, it's close, but the confidence interval is sort of in here. And it doesn't include 0. So that's additional evidence that that hypothesized value is wrong. If the hypothesized value was actually in the interval, which in this case means that the lower number would have to be negative, then we would have something inconsistent. But this is actually consistent with our model. Okay, so that's my confidence interval. Do the work though, because who knows, maybe I made a mistake. So do your own work and then check and compare against mine.